Okay, so on the first one, classify the following bonds as polar or nonpolar. Explain. So first, you find the difference in the electronegativity, which measures how tightly an atom attracts electrons. So across the top, I went and wrote all the electronegativity numbers and found out the difference. And then the difference tells you the bond type. So less than 0.4 is pure covalent, 0.4 to 1.8 is polar covalent, and more than 1.8 is ionic. So the atom with the delta negative is the more electronegative, and the delta plus is less. So for F and Cl, I have the delta negative for F, delta positive for Cl. It had a 1 difference for electronegativity, which would be polar covalent. And then for C and S, they had 0 difference, so pure covalent. For H and Br, we had a 0.7 difference, so polar covalent. I had delta positive on the H and delta negative on the Br. For B and H, I had 0.1 difference, so that would be pure covalent. And then C, L, and S, I had a 0.5 difference, so that would be polar covalent, delta negative on the Cl and delta positive on the S. For the Lewis structures, indicate the direction of the polarity of the bonds and which molecule is polar. So the CO2, I drew, let's see, the arrows going away from each other. It's linear, and the bonds cancel because the movement is in opposite directions, so it's not polar. And then on the H, the arrows kind of go up because the lone pairs bend the molecule structure, and the bends cancel, so that means it's polar. One example of a polar linear molecule and how it's different from CO2, I used the example from the book. OCS is linear like CO2. OC and CS have different electronegativity, so unlike CO2, they do not cancel each other out, meaning it's polar. So fill in the chart with the following Lewis symbol of each element. I wasn't really sure. I didn't really figure it out, so I started writing the electron configurations of everything, and then I couldn't remember the trends, but I ended up figuring that out. So the number of valence electrons just goes up across the period, so Li 1, and then the dot structure, I put Li plus 1 dot, and then Be 2, 3, 4, 5, 6, 7, 8 down the row, and then I gave just down the row each element the dots corresponding to the valence numbers. Let's see, how many valence electrons total are present in each of the following substances? So you just find the amount and then add them together, or the amount of valence per molecule and add them together. So S has 6, Cl has 7, and then 2 of those, so you had 20. HCN was 1 plus 4 plus 5, which equals 10 valence, and then CO4, 2 negative, so S has 6, O had 6 times 4 because there's 4, and then since it's ionic, you have to add the 2, so that would be 32 valence electrons. So up here it says the formal change on an atom equals the number of valence shell electrons minus the number of lone pair electrons plus half the number of bonding electrons. So calculate the formal charge on each of the atoms for CO. First find the valence electrons. So carbon plus oxygen is 10, and then you write the structure, which I have 2 dots on top of each other, C, the triple bond, O, and then 2 more dots or electrons. And to find that, you go the number of valence minus lone pair plus half. So the formal charge for carbon would have been 4 minus 2 plus 3, which equals -1, and then oxygen is 6 minus 2 plus 3, which equals 1. Okay, so I guess, yeah, I just wrote the structure for myself, I think. But, okay. On the table, complete the following table. I went through and I found the valence on each molecule, and then I think I wrote the dot structure next, and then that told me how many lone pairs and then the shape. So for H2O, I have 2 and linear. BF3, I have 0 lone pairs and trigonal. And then XeF4, I have 2 lone pairs, tetrahedral. PC35, 0 lone pairs, trigonal, bipyramidal, and SF6, I have 0 lone pairs and octahedral. For the last one, I went through and did all the valence again. I don't know if everybody does that or if you have to do that, but I think it makes it easier for me to understand. So that's what I did first. And then, so for the first line, I have 4, for CO2, I have 4 bonding electrons, 4 lone pairs, and then linear shape. BCl3, we have the trigonal shape, 9 lone pair and 3 bonding. NH4 plus, we have tetrahedral, 0 lone pairs and 4 of the bonding. H2O, tetrahedral, 2 lone pairs, 2 bonding. SF4, trigonal, bipyramidal, 1 lone pair and 4 bonding. And XeL4, octahedral, 14 lone pair and 4 bonding. And that's all.